All right, guys, so I'm going to go over a couple of the problems on this Chapter 14 practice worksheet. This is not graded. This is only for your benefit. Okay, so in Chapter 14 practice problem, the first one says find the oxidation uh, numbers for each of the atom in the following species. So I circled the ones that I kind of wanted to go over. So we have SO3. Now, if we recall, oxygen makes a -2 charge, right? And there is 3 of them. So that means we have a total of a -6 charge. But this atom or molecule itself, sorry, not atom, this molecule has a total charge equal to 0. So whatever this is going to be, it has to be 0. So x plus -6 is equal to 0. Add -6 to both sides. X is going to equal to +6. So therefore, sulfur is a +6, and oxygen is going to be a negative, actually a -2, but there is 3 of them. So I'm going to put a -2 there. But just keep in mind that there's 3, which gives us a total of -6, which allows this to be 0. Okay. All right. Those ones are quite simple, but go ahead and try them out. Let's do another one. Let's do these ones that are by themselves because they're by themselves, and sometimes we get confused. So an ion, a monoatomic ion with a charge on its own, is just going to be the same as its charge. So the oxidation state is a +1. All right. Next one says in each reaction below, identify the element that is oxidized and the element that is reduced. I'm going to go ahead and work with the hydrochloric acid and magnesium one. So aqueous solid, aqueous gas. So this is going to be a 0, and our gas also gets a 0. Okay, so gas also gets a 0. Aqueous, where we're going to have to decide, well, what is the charge on all of these? Chlorine is a -1, and hydrogen is a +1. When it goes over here, we have chlorine with a -1, but there's 2 of them, so we're going to have a -2 charge. And magnesium, in this case, is going to be a +2 charge with it. So now we get to move on and say, well, what's happening with everything, right? Actually, I'm not going to do we're just going to leave this as -1. Because then if I start putting those ones here, I'm going to have to add up all these molar values as well to this, and I'm just going to not add those. Make it simple for us. Simplify. All right. So chlorine -1, magnesium is a +2. What happens here? Well, hydrogen goes from a +1 to hydrogen 0, right? And this is gas, and this is aqueous. So positive to a 0 means a gained electrons, and if you gain electrons, you are reduced. All right. And now let's try the other one, chlorine. Chlorine goes from a -1 aqueous to a -1 aqueous. Chlorine, -1 aqueous. So this one is nothing happens. Nothing happens now. Now let's look at magnesium. Magnesium goes from a 0 in a solid state to magnesium +2 in an aqueous state. It has lost electrons. It became more positive, so therefore it is oxidized. Right? We ended up doing some half reactions there to try to figure it out. The next one is predict the products from these reactions and balance the equations if necessary. So we're going to predict products, magnesium plus bromine. This is combination reactions that are occurring here. So these are going to unite together to create magnesium bromide. Now remember that magnesium makes a +2 charge, so it can make 2 bonds. And we have 2 bromines, so it's going to work out perfectly to make magnesium bromide right there. And we didn't have to move or balance anything. The one that you might have to find a little trickier is going to be this one because it's a combustion reaction. And all combustion reactions are going to produce, I'll give you guys some help, they're going to produce water and carbon dioxide. Okay, so they're going to produce carbon dioxide gas and water. Okay, so all combustion reactions are going to produce that. So now your goal is going to be to make sure everything is balanced. All right, so now let's go into using the activity series to try to figure out if a reaction is going to occur or not. Lithium and potassium, we just did that in one of our examples. Actually, we did the reverse. So this is lithium solid, and we want to know if lithium solid is going to be able to replace potassium in an aqueous form. And we know this potassium is an aqueous form because of the positive charge that's right there. Okay? So keep in mind that all of these are going to be solids right here, all our metals, starting with. All right, so lithium's on the top. Lithium can replace whatever it wants, right? So therefore, we know that we're going to have lithium aqueous plus potassium solid occurring, and lithium's going to get that +1 charge. Okay. The other thing that we might want to add to these just to get used to it is, I was going to say, our electrons, but in this case, the electron just switched spots between these. I wanted to work on this one, the lead one. Okay, so lead and nickel nitrate, right? So let's find lead. Lead is right here. And let's find nickel. Nickel is right here. So lead solid cannot replace nickel inside of solution. So this is going to be no reaction. Okay. Finally, we have predict the products for the reactions of metals with acid and water and balance if necessary. So these ones right here. I'm going to go ahead and do the second one of nickel and hydrosulfuric acid. Okay, so we're going to be working on this one here. So when they combine together, remember you're going to get a replacement. So nickel and sulfate are going to combine together and hydrogen is separating by itself. So we're going to get nickel sulfate plus hydrogen gas, right, by itself. Okay. Hydrosulfuric here is actually known as sulfuric acid, and acids produce hydrogen gas inside of their reactions. I left a little space here because I wanted to see if we needed to balance this out. However, nickel makes a +2 charge and sulfate makes a -2 charge. So that means that there is no number between them. It's just a 1:1 ratio that's going to be there. Okay. Now we're going to balance this out. Two hydrogens, one sulfate, 1, 1. So everything's going to be a 1 to 1, 1, 1 ratio. So it actually balanced quite nice for us right there. Okay. All right. Next one, number 6 says, based on the activity series, which 4 metals do not generally react with an acid? So these are going to be our precious metals and precious metals. And I went over those on the last PowerPoint, which ones were our precious metals. So if you guys look at that towards the end of the PowerPoint, you're going to find out the precious metals that we have. Just think about what sells more at the jewelry store. Number 7, write a net ionic equation for the redox reaction shown below, then show the oxidation and reduction half reactions that take place. So these are actually my favorite. They involve a little bit more work to them, and I don't know, I like that. All right, so let's go ahead and break this apart as we best can. Magnesium is a solid, so in my net ionic, magnesium is not going to break apart at all. It's just going to stay as a solid. Now we're going to be looking at nickel, and bromine, right? So in this case, nickel is my solid. So nickel is going to be part of this. I want to erase things that are similar. So my spectator ions, the ones that have nothing to do with this formation of the solid, are the ones I'm going to get rid of, right? So solids have to stay, so that stays. Nickel is actually part of this solid formation, so that stays. Bromine is aqueous here. Bromine is also aqueous there. So bromine is my spectator ion, and it doesn't have any play in this. So I'm going to have magnesium plus nickel aqueous is going to give me magnesium aqueous plus nickel solid. Now I'm going to put the charges up on these, so you have to remember to put the charges. Nickel makes a +2 charge. Magnesium makes a +2 charge when it's in its aqueous state. And these are solids, so they're not going to have a charge, no oxidation state. So their oxidation state is going to be 0. All right, we're going to create half reactions, figure out which one's oxidized, which one's reduced. In case you forget, always write down Leo Gerd. Lose electrons, oxidize. Magnesium goes from a 0 to a +2, becomes more positive, so it lost electrons. So we're going to go ahead and write that half reaction of magnesium solid with a 0 charge going into magnesium aqueous with a +2 charge. And what we just learned in our other video is to include the electrons plus the 2 electrons that are going to balance that out to make a 0. Now we're going to do our reduction reaction. So in this one, we're going to have our nickel. I'm going to write nickel right over here. And it's aqueous. And that is going to turn into a nickel solid, right? With the oxidations of 0 and an oxidation of +2. Now the reason I left space here, yep, you figured it out, is because of the 2 electrons. So +2 electrons that go right there. So nickel is reduced and magnesium has been oxidized. Okay. All right, let's go into the half reactions and battery section. So don't be scared of this part. It has all these fancy words in it, voltaic cells and whatnot. It's all the same thing, just reworded differently. So use the voltaic cell diagram to complete the table below. This is called a voltaic cell. It's basically 2 solutions that are looped together with this metal rod, and it's a very specific metal rod. Actually, with the salt bridge, and these are my metal rods. Okay, the salt bridge helps with the ionization of it, right? So in our half reactions, my anode, which is the negative part, is zinc solid going into zinc +2 electrons, right? Now we want to know, well, what is going to be our cathode, right? Since it gave us an anode, I'm going to just assume that the cathode is going to be the other reaction. And in this case, we have Fe as our other reaction. So in a cathode reaction, all right, let's go ahead and write this down. We're going to have our iron, okay, and iron with the +2 charge because it's positive and it's aqueous, reacting and get our solid and our 2 electrons here. Okay. So we're just writing basically the half reactions of each, in which you noted that the anode started as a solid and the cathode started as an ion, right? The more positive one and the more negative one. So it goes from more negative to positive. So negative to positive, and this one went from positive to negative for our cathode. It's just weird how they write it out. All right, what role does the salt bridge play in this cell, you guys? So basically what it does, it maintains a neutral charge inside of the beakers. So where your ions are migrating towards the cathode part, and they're balancing out that extra negative charge. While the NO3s, the nitrates, are migrating towards the anodes to balance out the extra positive charge inside of the anode section, right? That's about it, is that it balances out the charge. See, that was for this question here. Okay, so it just balances and neutralizes the charge. Charge in containers. Right? So, like I said, the positive sodiums migrate towards the cathodes, and the negative nitrates migrate towards the anodes to balance out the different charges that are there. All right, lastly, balancing redox equations. So we want to be able to balance these equations. Let's go ahead and do this one right here. Magnesium, silver, and you're going to say, oh, they're all 1-1. They're all perfectly balanced. There is nothing else to do. Well, sort of, okay? What this means by balancing redox reactions, you want to balance the charges or the electrons, better yet. You want to balance those electrons. So here I have a 1 plus sign, +1. Here I have a +2 sign, right? You'll notice that the pluses don't necessarily match each other, and we need to make them match. So if I have a +2 here and only a +1 there, I need to make these match. So I'm going to put a 2 there to make 2 silver. So now I have a +2, +1 plus a +1, right? So I'm going to have a +1 and a +1, and that's going to be a +2, okay, charge. And magnesium's already a +2, so I don't have to do anything with that. But because I have 2 silvers there, I'm also going to have to put 2 silvers here. And remember, this is silver solid, so it has a charge of 0, so no matter how many you put there, that charge is going to remain at 0. So now our charges are balanced with these ones. Let's go ahead and do this one because we haven't really done the balancing of the electrons. So we have aluminum and nickel, and some more aluminum and nickel. So the +2 charge here and a +3 charge on this one. We want to balance those charges. So we have to find a common product between 2 and 3, the lowest common product actually, and that's going to be 6, right? So I'm going to have to multiply this by 3 to get 6. Multiply this one by 2 to get 6 as my positive charge. And now I have 3 nickels, so I'm going to have a 3 there for 3 nickels. And I have 2 aluminums, so I'm going to put a 2 there for 2 aluminums. And those charges are going to be nicely balanced. All right, you guys, that's it for these ones. You could go ahead and Google what is electroplating and what are fuel cells and all that. That's something that's easily Googleable. Or you could look into your textbook that also has that in the section 14.5. I hope this was helpful in assisting you.